Hey, all right, so today we're going to be going over phospholipids, sphingolipids, and acostanoids. So glad you're here. Go ahead and, well, since you're at home, go ahead and grab something warm to drink and we'll get going. So phospholipids, sphingolipids, and acostanoids. First up, let's talk about where we've seen these people and backbone, fatty acid, a phosphate, and what's called phosphatidate. And in order to make a tag, we would go take that glycerol and get rid of its phosphate and then add a last fatty acid, and that's a tag. To make a phospholipid, this same pathway branches. And we have a glycerol, and instead of taking the phosphate off of that glycerol, we leave it there. And then we will add a special fatty acid. There are lots of different kinds of special fatty acids. We'll take one of them and add it on top of the phosphate. And this is what we would call a phospholipid. You've seen these before in all those pictures of the cellular membrane, the lipid bilayer. A phosphate has this structure. It's got a phosphate atom, phosphorus atom in the center, and then it has 4 oxygens, extremely electronegative molecules, attached to it. That means it's got 4 negative charges in one phosphate group. Those charges, water likes charges, and so that makes it very hydrophilic. So this glycerol keeping a phosphate means that now it has 3 hydrophobic things that are fatty acids, very hydrophobic, trying to get away from water, and then phosphorus, a very hydrophilic thing. And that lets us have a membrane, a lipid bilayer with molecules, one side which is near blood and plasma and other watery charged type substances, and the phosphates will go towards those. And then hidden behind the phosphates, we're able to have all the hydrophobic, all done with a single class of molecule. One that has both very hydrophilic and very hydrophobic portions, all in one package. So phospholipids are really important for membranes and for a number of other things because of these properties where they have both hydrophilic and hydrophobic properties. So now we are going to go into what are the specific kinds of phospholipids, because you can have a lot of different squiggles added right here. You could have things like choline or serine or a bunch of other things, and that'll change the exact function, but it's still going to be hydrophilic in one place, hydrophobic in another. So that's phospholipids. Sphingolipids are similar to phospholipids. They just use a different backbone, as we'll see. And then acostanoids are going to be some of the specialized uses of phospholipids and sphingolipids when you pop off the stored squiggle bits, the stored fatty acids, and use them for things like inflammation. Acostanoids will do that. You take a bit off, and then you go ahead and use it for the inflammation response and clotting cascade and things like that. You actually use things that are stored on the phospholipids. So if you didn't have phospholipids, besides membranes and all the other things that we've talked about, you also wouldn't be able to do the inflammation response because your storage of precursor molecules would be gone, because this is where we store them. All right, so that's why it's important. Now let's go ahead and hop in for getting into it. For phospholipids, we've seen where they come from. Now, let's go ahead and see what kinds we have. So, first up, as we mentioned, a glycerol backbone, which is a sugar that says glycerol, 2 fatty acids, and a phosphate. All of these together are called it has a special name because this backbone molecule is the same for all of the phospholipids. And so this backbone molecule being the building block, it got a special name, and that is, as we mentioned, phosphatidate. Now, if you see phosphatidic, it's just the difference of the acidity of the solution it's in, and therefore whether or not it has a hydrogen or not, same molecule. Okay, so phosphatidate, phosphatidic acid, same thing. This backbone can have a number of different phospholipids being built off of it. So let's go into those. You can have phosphatidyl inositol, phosphatidyl ethanolamine, phosphatidyl choline. Oh, and by the way, PS, you can have phosphatidyl serine. And I'll write all of these out in a little bit, but if you write them in this order, I wrote them from bottom to top, but it doesn't matter. If you do phosphatidyl choline, phosphatidyl ethanolamine, phosphatidyl inositol, PC, PE, PI, and then phosphatidyl serine, PS, off to the side, it'll make it easy for you to see how you can do a, you can remember how they are made, like what can be made from something else. So let's go into it. From phosphatidate, there are 2 ways that you can make any of these first 3 guys. To make them, you need to have something called CDP, cysteine diphosphate, and then you need to have whatever fatty acid we're talking about, choline, ethanolamine, or inositol, any of those. And that's what this represents, either choline, ethanolamine, or inositol. And then you need to have the phosphatidate. And the 2 ways they consider this 2 separate pathways, if you think of the CDP as a sticky bit, you can either take the CDP, stick it to the phosphate, CDP, and then stick the fatty acid onto the CDP next. So it would be this plus the fatty acid next. That's one pathway. This would be called a CDP activated phosphatidate because it got a CDP first. The second pathway for making this is almost the same thing. I'll go ahead and draw in blue for this. There's our glycerol, there's our squiggle, there's our second squiggle, there's the phosphate, and we could have CDP, our sticky molecule, CDP, and it's already got the choline or ethanolamine or inositol attached to it, and then you take that whole clump and attach it to the phosphate. And they consider these 2 separate pathways. This one, the CDP stuck to the glycerol, and then that was what happened first, and second, you put the fatty acid onto the CDP. Pathway 1. Pathway 2, CDP sticks to the fatty acid first, and then the other end of its sticky bit second sticks to the phosphate. The reason they have these separate, I believe, is because you can regulate them differently, but it is pretty simple. It's like stick this Lego together and then this one, or stick this Lego together and then this one. Stick Lego A together first or Lego B together first. So those are 2 pathways that can be made, and if you made this inositol. Now, how else can we make this? We can make this by actually, phosphatidyl ethanolamine is really good at sharing, really good at converting. And this is actually the only way to make phosphatidyl serine is to first make phosphatidyl ethanolamine. Once the phosphate is grabbed on, or the CDP is grabbed onto the ethanolamine, it converts in shape just a little bit, and then you can scoop out the ethanolamine and put a serine in, where you can't do it directly. But once you make that kind of a shape change, you can go ahead and there's an enzyme that can swap the two with that adjusted shape. So ethanolamine can be swapped for phosphatidylcholine, also can do the same thing with phosphatidylcholine. This is a little less important because we can directly make phosphatidylcholine, but hey, it's good to know. So with this is how you make the basic structures of the phospholipids. Now, let's go ahead and say, what are these good for? All right, so we have phosphatidylcholine. We have phosphatidylethanolamine. We have phosphatidylserine. And then we have phosphatidylinositol. Choline. Choline, as it happens, phosphatidylcholine, is going to be very good for two things. Surfactant in the lungs is one of them. Surfactant. So you might be familiar with or have seen a child, a newborn baby, taking their very first breath. And it's really hard to take that first breath, and it's like this gasp when they manage to get it in. What's happening is that at the beginning, when the baby first comes out, all of their lungs have been squished because they've been in a very small space, and all the alveoli, or little air sacs at the bottom of the bronchioles, bottom of the airways of the lungs, where gas exchange happens, all of those kind of ping pong balls were completely closed. And there was liquid lining those, and that liquid, if you think of a drop of water on anything laminated, you can see the water bead up instead of spread out. Water likes to hold on to itself. That happens in the alveoli as well. There's water or liquid coating the alveoli, and it likes to hold together, and that draws the alveoli closed. So the baby's trying to take a breath, and it has to break that surface tension. The water holding to itself is actually surface tension of the water, and open it up. And that takes a lot of muscle. Baby keeps breathing. Everyone's happy. It's great. Why doesn't it close back up? Because water likes to come together. It should. The thing that prevents that is surfactant. Surfactant breaks the surface tension of the water. And after baby takes its first breath, what keeps it from having enough surface tension to pull closed again is that we have phosphatidylcholine, which we call surfactant in the lungs, keeping the alveoli, the liquid lining, from holding to itself too much. If baby doesn't have surfactant and phosphatidylcholine, then baby's second breath and third breath, and baby will eventually get exhausted. And trained medical personnel, which we aim to be, would be able to see this and say, that baby hasn't been able to make surfactant. You just take some surfactant and squeeze it down the baby's airway, and then you would rush them off for something more long-term, but that would take care of it for a little while. This can also happen in adults, but not as common. Basically, if you can't make surfactant, it gets kind of hard to breathe, and you can exhaust yourself just by trying to breathe. So phosphatidylcholine is good for surfactant. The other thing it's good for, myelin. Nerves are coated in myelin, and that makes their action potentials travel faster down the axons. It's an insulation. So if you think of cords coated in rubber or any other sort of insulation material, if you took that off, then electricity would move down those cords much slower, and a lot more of it would be wasted, and there'd be a lot more resistance, electrical resistance. Myelin gets rid of that resistance and thereby lets the action potential, which is basically, it's charge, so it's basically electricity, move down the axons much faster. So choline is good for surfactant and myelin, among other things. Next, ethanolamine. Ethanolamine is good for membranes. They're all good for membranes, but ethanolamine is especially good for membranes, and so is phosphatidylserine. So I'm just going to put ditto marks membranes. And these two guys that do kind of the same little shtick, same deal, they also are in the same subfamily. All of these are phospholipids. However, ethanolamine and serine are called a special family of phospholipids, and they are called cephalins. Cephalins, cephalins. So both of them get put into the phospholipid bilayer of membranes and help make up the membrane. Just as kind of a structural thing, they're not there to be pulled apart and made into surfactant or sent off somewhere to be made into myelin. Or what inositol does is it lives in the membrane like all these guys do until it's needed and pulled out. And this one we've seen before in physiology. And this one is going to be a secondary messenger. So you might remember let's draw a membrane here. Squiggle bit, squiggle bit, squiggle bit, squiggle bit. All right, and you have a G protein turned on. It goes over, turns on phospholipase C. Phospholipase C grabs something out of the membrane. Turns out it's phosphatidylinositol, and it cuts phosphatidylinositol in half. And if you cut it in half, then you have a diacylglycerol, two acyl groups in a glycerol. This is DAG. And the other half, you have inositol, and it's got a bunch of phosphates on it, triphosphate, IP3. IP3 goes down and opens up the calcium from the endoplasmic reticulum. DAG will go and turn on protein kinase C, and then they do a bunch of stuff. But what we want you to remember in biochemistry at the moment, that's kind of moving into an entire pathway. Just to remind you, that was covered in physiology. It's touched on biochem as well. But what we want you to remember is inositol was part of that secondary messenger system. So, again, choline, good for surfactant and myelin. The cephalins, which include ethanolamine and serine, those are good for kind of the standard membrane, keep the membrane together. Don't cut these guys up too much. Inositol, or phosphatidylinositol, is good as a secondary messenger. So sending messages further into the cell and make a cascade of messengers grow. All right. So now these are kind of the standard phospholipids. And now I want to tell you about two phospholipids that are a little bit more interesting in the fact that what you're attaching isn't just a lipid, okay? So we've done two things: how to make your standard phospholipids, what the standard phospholipids do. There are more of them, but this is a good beginning example. Next, what are some of the non-standard? By my terminology, I call them non-standard. That's not necessarily from a textbook calling them non-standard, but they don't have a lipid just stuck on the end, which makes them different. Let's see if you guys can see green. You can't. I'm going to set green aside. All right. So we had our first box, we had our second box. Now let's go ahead. We have a phosphatidate right here. As I draw my beautiful angular drawings of modern art, we have a phosphatidate, and in its open spot, we're going to add a glycerol. So we just stuck another glycerol there, which is a sugar backbone. If we throw a glycerol there, then this is going to be phosphatidylglycerol, or PG. Its main job is to be a precursor to the next guy that I'm going to show you. So that's all he really is. He can do a few other minor things. I think he can help out with surfactant, but that's not really like his thing. His thing is being a precursor to this next guy, and this is going to be diphosphatidylglycerol. Di meaning two, phosphatidyl because it has a phosphatidate. There are two phosphatidates, and then glycerol because it's going to have a glycerol on top of one of the phosphatidates. So what does that look like? Well, here's our phosphatidate, two fatty acids, phosphate, the glycerol that we added on before. Here's the new stuff. I'll draw in another color. We throw a phosphate on right there, and another glycerol, and two fatty acids. What is this? The phosphate is drawn on the back, but this is just another phosphatidate group. So we got one right here, and one right here, and then a glycerol between them, holding them together. Diphosphatidylglycerol. Glycerol. See what's going on there? So diphosphatidylglycerol is really important for, well, frankly, it's used for almost everything except as a secondary messenger. It's used in surfactant, it's used in myelin, it's used in membranes, and a number of other things. I don't know of it being used as a secondary messenger. That's its one thing that's not going on. So this is kind of the not sticking a lipid on, but sticking something else on. So that's the phospholipids. Next, if you wanted to go ahead and pause and review those three chunks, how do you make it? What does it do? How do you make the special guys, and what do they do? Then go ahead and do so. Let's power on to our second chunk. I'll go ahead and leave some of this up as we go to sphingolipids. All right. Sphingolipids are very similar to phospholipids in structure, except their backbone looks like this. It is not glycerol. And that's one of the main things that you want to take away from this difference is the backbone is a sugar that's in the shape of an L, and it's not called glycerol, it's sphingosine. And you'll notice that the first spot of the three spots is taken up by the sugar itself, and so you only have room for one squiggle right there, and then you're down to the phosphate spot. Now, if we take this whole collection right here, this, like a phosphatidate, is going to have a special name because it's the backbone of most of the sphingolipids. And this is going to be a ceramide. Ceramide if it doesn't have the phosphate, phosphoceramide if it does have the phosphate. So ceramide like this without a phosphate. All right, sphingosine backbone. Instead of calling it a phosphatidate, we call it a ceramide. All right, now what kinds can we have? If we throw the phosphate back on there, let's take it out of the thing right there. If we do this, have a phosphate, and we throw on a squiggle, and that squiggle is called choline, this would be called the molecule sphingomyelin. And sphingomyelin, in its name, tells you what it does. What did choline do in our past thing? It's right there. Whoop. All right, it's going to be used for myelin. So, sphingomyelin, phosphatidylcholine, both are used for myelination. This is our one sphingophospholipid that we'll talk about. Now let's talk about glycerosphingolipids. There are three that we care about, three classes, three families. And they are called globo, cerebro, and gangliosides. So globoside, cerebroside, ganglioside. I like to just kind of think of on a beach, you found a globe that was washed up. You walked a little further. You found a jar with a brain in it, cerebroside, so cerebrum in a jar. And then there was a gang member who came, and we're not going to draw very well for this one. So there we go. He's a gang member. He says hello, and he's got a bandana on. Okay. Now, what are the differences between these? Globosides. Let's go back up here. Globosides would have one sugar. Cerebrosides would have two sugars. And gangliosides would have two. They would also have two sugars plus a very special acid. And that acid is called, so I'm going to make acid a little squirrely cloud up here, sialic acid. So going back to the beach, if you imagine you're on a beach and you're going by and it's like, oh, look, there's a globe that's washed up. Maybe there's a shipwreck nearby. Oh, look, there's a brain in a jar. Must have been an interesting cruise. And, oh, look, there's a gang member at the end of the pier. He jumps off into the sea. And so gangliosides have sialic acid. Sialic acid as their additional molecule. So to recap, globosides have one sugar and then some kind of fatty acid. Cerebrosides have two sugars and then some kind of fatty acid. Gangliosides have two sugars and sialic acid as well as some kind of fatty acid. Those are glycerosphingolipid subcategories, and it's just good to be aware of them. You can go ahead, there's interesting functions that you can find inside each family, but those are beyond the scope of what we're going to go into today. All right, so that's sphingolipids. Let me know if there are any questions, and if not, let's go ahead and move forward to our third topic. Oh, and for review, what I do is pause. What are the sphingolipid backbones? Ceramide, sphingosine. Can you talk about the backbone? Second, what was the one sphingophospholipid, or phosphosphingolipid, excuse me. And then 3, try and review what were the glycerosphingolipids. And glycerosphingolipids don't have a phosphate in them, okay? So you pop that phosphate off and stick in the sugar and perhaps sialic acid. Go ahead and review each of those 3 chunks if you want. We're going to move on. All right, now, Acostanoids. Acostanoids play roles in inflammation. So they're kind of part of the phospholipids, but we're going to be popping bits off of the phospholipids and then using them for inflammation-related activities. That's what makes them eicosanoids. Okay? So similar to how you could classify mammals as one way of classifying things because they all have these things in common, you could also classify things by, they have 4 legs. Some things that are mammals have 4 legs. Some things that are insects have 4 legs. Eicosanoids are not being classified on structure like these other 2 were. They're being classified on action. And that's why there's like this weird overlap that some people can find, like if you're trying to do it by structure still, it can get stuck in your head. So this is by function, eicosanoids. So, and that function is relative to inflammation. So eicosanoids, in order to make the most important eicosanoids, we need to have a precursor molecule that we actually can't synthesize in our body. We have to eat it. and that is going to be linoleic acid, or omega-6. There are a lot of different kinds of omega-6. We can't make any of them, so we need omega-6s in order to make these molecules. And in our standard diet, at least here in the US, wherever you might be, we tend to get a lot more omega-6s than we need, so this isn't something that usually people run out of. But it is an essential fatty acid. Let's go ahead and write it out. Linoleic acid, aka omega-6. And since we're talking about omega-6, I'm going to throw omega-3 in as well. It is not part of the pathway we're talking about today, but just for knowledge's sake. Linolenic acid. This is omega-3, the omega-3 family. The way I like to remember it is there is only one letter of difference between the two. Linoleic, linolenic, you just throw an extra N in, and that's the omega-3. And the way that I remember it's this one, the extra N has 3 points on it when you draw it. Like if you just look at the letter N, it's like, oh yeah, it's got a point right there, it's got a point right there, it's got a point right there. It's got 3 points. The one that has the extra letter N in it is omega-3. That's how I remember it. Hopefully that helps you. Okay. If not, you can remember, it was really weird the way Taylor remembered it. And so that was weird enough that I remember Taylor remembering that it was linolenic. You can do it that way. If it doesn't work, that could be memorable too. All right, so now that I'm not done being ridiculous, but at least done for the moment, linoleic acid is our precursor molecule for one of our major eicosanoids, for the active molecule. What is that molecule? Sounds like a spider, arachidonic acid. All right, kill it with fire. So that's actually how you can remember it if you want. I actually had never thought of that before, but it's like spiders, kill them with fire, there you go. Anyway, arachidonic acid. Now, arachidonic acid can be, once we make arachidonic acid, we're going to stick it onto phospholipids that are going to be in the membranes of pretty much every cell in the body, so that we're going to have arachidonic acid at hand no matter where we are. So if we get a cut, that skin cell, its membrane, has arachidonic acid as part of a phospholipid. So let's go ahead and draw a phospholipid. We got 1 squiggle, got 2 squiggles, got a phosphate, and then 3 squiggles. What kind of phospholipid is this? I don't know. And it doesn't really matter, because this phospholipid could be an ethanol, a phosphatidylethanolamine, could be phosphatidylserine. Whatever it is, some phospholipids will have in their second slot arachidonic acid. And so if you pop that off, there's your arachidonic acid right out of the membrane. How do we pop it off? All right, let's pause the pathway. Linoleic down to arachidonic, then we're going to talk about where it goes. But when we need it, how do we pull it back off? We already talked about in another video when we were making tags that we put it on with glycerol 3-phosphate acyl transferase, G3P-A transferase. But how do we pull it back off? It's not that same enzyme, actually. And these enzymes are the ones that you want to learn today, I presume, at least that we're aiming to learn through this lecture. To remove any of these bits, whichever one you might need, there's a family of lipases, and they have very simple names. You have A1 that will cut right here and take off the first fatty acid, whatever it is. Doesn't matter what it is, it'll just cut off right there. It's a pair of scissors. That's A1. Then you have A2, which is the one that'll take off our arachidonic acid. Arachidonic acid is stored at the second spot. If it's on a phospholipid, it will be on the second spot. Not on every phospholipid. But if it is there, spot 2. And that's A2 that will cut it off. And then our next one is going to be C. Oh, geez. C, which will cut right here. Now, I'm going to go ahead and move you guys a little closer so you can see this. Ha ha ha, pun not intended. You can go ahead and take a look. It's cutting before the phosphate. So you'd cut off the phosphate and the phospholipid. Our last lipase is just called D, and it cuts off after the phosphate. And so then you would leave the phosphate on the glycerol, where the fatty acid is then allowed to fly free by itself. Those four, A1, A2, C, and D, are the family of single acyl lipases, single acyl lipases to take off any particular phospholipid that we need, or any particular lipid we need off of the entire phospholipid. We also use these in digestion. So we dump a bunch of these in. Lingual lipase is a type of A1 lipase, as an example. Whereas pancreatic lipase is a mixed lipase that actually takes care of 1 and C. All right, so now that we know how to get the arachidonic acid both on and off of the phospholipid, how do we use it in inflammation? We know it's in every cell membrane, and so it's always available. If we get a cut and we want to start the inflammation response to kill any bacteria that might be getting in there, and we want to call the immune system to us, arachidonic acid can be pulled off with A2, and then that arachidonic acid will be acted on by more than two, but two main families of enzymes. Family 1, COX-1 and COX-2. These guys are responsible, so if they cut up the arachidonic acid in their special way, if they adjust it, then COX-1 will make thromboxane, which helps with platelet and coagulation activities, whereas COX-2 will go ahead and do these other guys, which are going to be prostaglandin, and that's a whole family. There's prostaglandins, there's several of them, and also prostacyclin. All right, COX-2 has these two things it makes. COX-1 has this one thing it makes. There are more than just those, but for now, those are like the core ones. You can remember it that way. I said that there were two pathways away from arachidonic acid. What's the other one? The other one is it gets acted on by an enzyme called lipoxygenase. And that will make molecules called lipoxins, as well as leukotrienes. So LLL from the lipoxygenase, and then COX-1 and 2. 1 makes the thromboxane for clotting. 2 does the inflammation molecules, prostaglandins, as well as prostacyclins. Those are our acostanoids. The way that I would review this is, first, what are the omega-6 and omega-3s, how do you tell them apart, and acostanoids being made into their base molecule from which of them? Linoleic into arachidonic. That's number 1. Go over the basic, how do you make arachidonic acid? Number 2, how do you pull it off? What are the lipase names, A1, A2, C, and D? And then number 3, what are the two enzyme pathways, COX, lipoxygenase, what do they make? And that is how we would go over the phospholipids. So thank you for joining us. And I noticed that there is, for anyone viewing, are there any questions that you wanted to hit before we tie up? Not seeing anything coming in, so I'll just give you a few quiz questions and then we'll go ahead and end our stream, and we'll pick up another stream on the hour for physiology. So for biochem, looking away from the screen, so that's what it looks like, and now looking away from the screen. Quiz questions, I would ask, what is the backbone? What is that sugar called? All right, it's glycerol. What does phosphatidylcholine get used for? There are two things. All right, one of them, remember the baby? One of them is surfactant. Number two, myelin, for removing electrical resistance so that you can have faster movement of action potentials. That's phosphatidylcholine. What is a ceramide? Like, what is it? Can you either draw out a structure, give a definition, just something that shows you know what a ceramide is if it was put to you in some sort of paragraph form question? All right, a ceramide is, it's got a sphingosine, not a glycerol, a sphingosine backbone, as well as one acyl group, and then that's a ceramide. If you added a phosphate to it, it would be a phosphoceramide, but no one cares. So there's your geekery. But yeah, and it's one of the sphingolipid, it's a sphingolipid backbone. Kind of like phosphatidate is for phospholipids, ceramide is for sphingolipids. All right, another question. What does it take to make something a ganglioside? Okay, it would be a ceramide plus 2 sugars and a sialic acid. All right. Which of the following is part of the is not part of the inflammation pathway? Oh, I shouldn't say that because they do play a role elsewhere. We didn't. Okay. Which of these is an omega-3? Linoleic, linolenic, or arachidonic acid? Linolenic with the extra N, that's our omega-3. And linoleic then is the one that is the precursor to arachidonic acid. Where is arachidonic acid stored, and how do we get it out into use? It is stored on phospholipids in the second spot. An A2 class enzyme, lipase, will cut it off, and then we have it getting used by various other enzymes, COX or lipoxygenase. All right, I'm going to go ahead and end this stream with a fun fact that I recently found a really cool research article on omega-3s, and where omega-6s are increasing the inflammation, which is good to a point. Omega-3s actually help regulate the downregulation of inflammation. So for psoriasis, for example, that's having, you have inflammation going a little bit too much and it causes skin issues and things like that. If you take omega-3s, then they are put onto the second spot of phospholipids as well. And so they compete for the omega-6s. And so then when you have more omega-3s, less omega-6s get put on there. When something gets cut off, there's a higher chance of it being a turn down the inflammation response. And psoriasis has had convincing clinical studies of taking omega-3 supplements, reducing incidence of psoriasis, likely because of that pathway, where omega-3s compete with omega-6s, and arachidonic acid being the derivative of the omega-6. And so sometimes you cut it off and you get something that lowers the inflammation instead of if you have 10 times as much omega-6 and arachidonic acid as you do omega-3s, you cut it off, it's probably going to continue making it worse and worse. And we're supposed to have it in a ratio of 1 omega-3 to 4 omega-6s, roughly, maybe 1 to 2. And what most Americans have is 1 to 10 or 1 to 20. So, with that fun fact, eat your omega-3s might help you with various issues, and also membrane fluidity, which is every cell in the body. Thanks for coming, and good luck. Go be an amazing doc. The world needs us.